as we go on. So, they say the oscillation, and oscillation is simply a regular, repetitive, to and fro motion. All right? Now, somebody's sitting on a swing, and you push them along, that's also an oscillation. All right? If I took let's say it's a swing, or it's a pendulum, it can also do the same thing. If I lift it up, and I let it go, this pendulum or oscillating system is going to vibrate, oscillate, at a specific frequency. Because if I just give it a single displacement and it starts vibrating, we say this thing is vibrating at one of its natural frequencies. Now if you're in a swing, and they lift up the swing and you start swinging backwards and forwards, eventually what's going to happen? It's going to run down, you're going to stop. If I wanted you to keep on going, I would have to push. But with a specific rhythm, okay? If the frequency with which I push that swing is the same frequency as the vibrating system, we are going to eventually get the amplitude of the vibration to increase. And that is what we saw with the Tacoma Narrows Bridge video. What happens is, if I have a vibrating system and I force a vibration, but it has the same frequency as that object that is vibrating, we find that the amplitude of the vibration will increase. And if we keep doing it, it will keep on increasing. And that is why the bridge eventually broke. Initially it started vibrating at one of its natural frequencies. But on that specific day, the speed of the wind caused a vibration that had the same frequency as one of the natural vibrations of that bridge. And it caused the amplitude, because you see the bridge doing this, it caused the amplitude of the vibration to increase. When we looked at the video clip on the Barton pendulum, we saw that, let's just take another page, we had a string there, stand there, and we had little weights hanging from the string, and then we had one heavier object. And all of them were standing still, and they displaced this one, and it started swinging backwards and forwards. The vibration is transferred through the string, and all these other little weights started swinging backwards and forwards at their own natural frequency. One of the weights started increasing the amplitude of its swing, because the frequency of the forcing, the one forcing the vibration, was the same as the frequency as one of the weights. And that one will start swinging with an ever increasing amplitude. We call this resonance. When do we get resonance? When we have a forcing frequency equal to the natural frequency of the object. We find that the amplitude of the vibration will increase. When I was a child, young, where we lived was there near, it was in Cape Town, but it was near to the, not near to the airport, but the aeroplanes that would come into land flew directly over our houses. And it was in the time of the Concorde. Now the Concorde is a much faster aeroplane than the others. And he has to come in fairly low because they're coming into land. When the Concorde comes in, they say to us, open your house windows. Because the supersonic jet is going to cause a vibrational frequency that if you do not somehow cancel that vibration, it's going to vibrate more and more and more, and it's going to shatter the glass. When there's an earthquake, I don't know if you've ever seen the pictures after the devastation, you see heaps of bricks and rubble as the houses collapsed, and then sometimes there's this one little lonesome building standing upright as if nothing had happened. Have you ever seen a picture like that? Yes. Why did the one building not collapse, but the others did? No. When there was an earthquake, the earth is vibrating. All right? When that vibration reaches the natural frequency of the building is going to vibrate with an ever increasing amplitude. Which are the ones that shattered and fell down? Those buildings, not necessarily the tallest, but those buildings where resonance started occurring. The one that remained standing, what happened? Was there any resonance? Probably not. Or if there was some other system that could cancel it. When they build buildings in Japan, lots of earthquakes there, they build them earthquake safe. How do they do it? They build into the structure, the engineering structure, they build in a damping system. And it's as simple as, for example, now the engineering itself is not all that simple, but for example, if I had a tall building, all right, and in the top, I put a tank full of water. If the building sways in that direction, what does the water do? It tends to stand still, but when the building comes back, the water moves in the opposite direction. So it cancels the vibration of the building. They can do similar ones, something similar to that can be done if you hang a heavy weight. If the building shakes to the one, the weight comes after a while, and then it shakes back, and the weight cancels the movement. It's damping the motion. Well, it depends. They don't normally do that at this point. Or, into the foundation, they build a system that if the earth shakes in that direction, the building goes in that direction, and when the earth comes back, they do that. It cancels the vibration. We say damping occurs. If I looked at it in terms of waves, well, if this was the vibration, the damping cycle has to be 1/2 wavelength out of phase. And it will cancel the vibration. You follow? Okay, so let's check in your books. They start off, they're on page 341. This is higher level only, oscillations. They say periodic movement in which a pattern of movement is repeated over regular periods of time is very common all around us. Then they say the pendulum is a simple oscillator. If you start a pendulum oscillating, in other words swinging, it will continue oscillating forever unless it is damped. Now, it makes me think of these perpetual motion toys that you get. Very little friction on it, so you lift the little ball up, it will swing backwards and forwards forever. All right? Unless there was some friction that could damp the movement, which eventually does happen. All right? Every pendulum will oscillate at its own natural frequency. Just have a look at this thing. My pendulum if the string is this long, that so many cycles per second would be the frequency of this oscillator, the natural frequency. If I shorten the string, can you see that the frequency is higher? Okay. So every single object, and it's, well, if it's a pendulum, it's got to do with the length of the pendulum that will determine the natural frequency. But buildings, because they are much more complex, have usually got more than one natural frequency at which it can vibrate and then start resonating. So when they talk about a natural frequency, it's just very simply the frequency at which something vibrates after one. If I take my page and I displace it, well, that's the frequency. Why does this one not keep swinging there and there and there and there? Yes, I've got lots of surface area along, and there's some air friction. All right, that's why this one is damped after 1/2 cycle. Okay. Yeah? Yes, then it should keep going. All right, because there's no friction. Unless the elasticity of the material over here where it goes backwards and forwards. But if I could attach it in such a way that that there wasn't friction there, it should keep swinging. Okay. They say you have studied the movement of a pendulum and you have found that the frequency of a pendulum depends only on its length. It does not depend on the mass, and it does not depend on the size of the initial displacement. In other words, here I have my string. I've got a mass piece on the bottom. That's the frequency of the vibration. If I would remove this mass piece and add a smaller mass piece to it, a lighter one, is it going to affect the frequency of the vibration? No. Okay. Whether I displace the weight to there and let it go, or whether I displace the weight to there or let it go, does it affect the period? Nope. The only factor that affects the frequency or period of this oscillator is the length of it. All right? If it has a length of 1 meter, the period will be 2 seconds to go from there to there and back to there. It will be 2 seconds. Okay. Then on the next page, they try and explain that the vibration of the oscillator can be sort of translated into a graph that looks like that. Okay? If I have an oscillator, let's say I have a bucket and I've got a hole in it and I fill the bucket with sand and I set it swinging like this and I pull a sheet of paper underneath it, the pattern that will be formed on the paper will look like that. All right? Because from there is the 0 position to a maximum, there, back to 0, there, to a maximum in the opposite direction, there, all right, back to 0, there, maximum in the opposite direction, there we go. Do you understand? So we can translate a vibration into a sine curve. And from that we can determine wavelength and period and frequency. All right. You must what? I don't know about that one. But okay, let's carry on then. Now they say, from the table, you can see that the velocity in simple harmonic motion is varying in the same way as the displacement. Listen. Here's my pendulum. This is very important. This is high-level work. If I look at this pendulum, let's say it starts moving over there. What is the speed over here? 0. The speed over here? Maximum. The speed over there? 0. Over here? Maximum. Over there? Okay. So, if I... Seriously? All right. The red graph is my pendulum swinging. All right? And I want to start it over here. Let's just start it on the 0 position. Okay. No, I need to start it on the maximum. Okay. All right. So my pendulum is displaced. Maximum displacement. What do we know about velocity? Okay, so here we have displacement. Here I have velocity. So when it's at maximum displacement, what is my velocity? 0. There we go. All right. Now it's going to go faster, faster, faster. Maximum velocity, ne? All right. So, well, if this is the displacement over there, here we have 0 displacement, but at that point we will have maximum velocity. All right. So now it goes up on the other side. What happens to the velocity? 0, but the displacement is maximum. So there. All right. Can you see? Yes, I think it's actually going to go in the opposite direction. My graph should actually look like this. Let's do it there and there. Okay. Over here, we have 0. Over there, I should have maximum. Over there. Over here, I should have 0. No? Okay, so we will get the graph to look like this. No, I was right the first time around. No. Yeah. What is this distance? No. No. It's half a wavelength. It's not half a wavelength, it is quarter of a wavelength. Okay, so when the displacement is maximum, the velocity is 0. When the displacement is 0, the velocity is maximum. Now listen to, if I read the sentence that they say. They say, from the table you can see the velocity in simple harmonic motion is varying. All right, from, well, maximum 0 velocity, maximum 0, maximum. They say in this, it's varying in the same way as the displacement, but it is 1/4 of a cycle behind. All right? And we say that the displacement and the velocity are out of phase with each other. They are out of phase by 1/4 wave cycle. Now, I want to show you something. I actually want to clone this thing. Okay, here we go. There. The wave cycle is 1/4 wavelength. 1/4 wavelength out of phase. You see that? That is what the graph should look like. So I should actually, yes, it is right. All right. So it will go there and there and there and there. You follow? Sien jy dit? All right. Now, if we go and have a look at the acceleration of the pendulum, all right? Gravity makes it accelerate. The acceleration, yes, is going to go. Positive acceleration is going to go faster, 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 fastest. And now, negative acceleration, slower, 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 slower. Then, positive acceleration, faster, 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 faster. Negative acceleration, slower, slower, slower. So what happens is when you go and look at the curve, then we find that the acceleration also has a sine curve shape. But when we draw the acceleration, we need to draw it 1/4 wavelength. There it would be on it. So 1/4 wavelength out of phase. There we go. So what does the acceleration look like? I'm going to take it away. The acceleration would be the exact opposite of the displacement. So our acceleration graph would look like that. Sorry, my amplitude must be more or less the same. So we say, when we have simple harmonic motion, regular repetitive to and fro motion, we say that the displacement time, the speed time, and the acceleration time graphs, they lag a quarter wavelength behind. So velocity time will lag a quarter wavelength behind the displacement time. And the acceleration time lags a quarter of a wavelength behind the velocity time, which makes it a half wavelength behind the displacement time. Okay, this is there on the next page. No, that's about it. All right, on the next page, I just want to go through it with it. There they explain figure 13.4. Velocity is maximum positive when the displacement is 0, just from the little graph there. And then they say, how does the acceleration of the bob change over the cycle? And if you go and look at figure 19.5, there you will see they show that the acceleration lags a quarter wavelength behind the velocity time graph. They say in simple harmonic motion, the displacement lags behind the velocity by 90 degrees. Why 90 degrees? It's a quarter of a wave cycle. All right. Now, circular motion, if I had a piece of paper that was moving, you get a graph, okay? So a quarter cycle is 90 degrees. So they say then, ek lees weer, in simple harmonic motion, the displacement lags behind the velocity by 90 degrees, and the velocity lags behind the acceleration by 90 degrees. Okay. Forced oscillations and resonance. Just very simply, there they have the picture of Barton's pendulum, and below that picture one, the second paragraph, you will find that eventually the pendulums will all oscillate at the same frequency, but they will vibrate with different amplitudes. And then which one will the amplitude increase? The one that has the same natural frequency as the forcing frequency of the weight, and we find that the amplitude will increase. This is resonance. Okay, forced oscillations. All pendulums will oscillate with almost the same frequency despite their length. The frequency is not the natural frequency of the pendulums. The oscillations were, in other words, forced. It's interesting to note that these oscillations were quite small. All right. On the next page, there, yes, we've done it. It's resonance. It's just the definition of the resonance is there. They say, we usually only notice forced vibrations when they cause resonance. All right. Resonance happens when the forced vibration happens to be the same as the natural vibrating frequency. It's like a swing. If I force it at the same frequency that it is swinging backwards and forwards, it's going to go higher up with each push. They say, yes. Then they say, resonance happens when a forced vibration happens to be the same as the natural vibrating frequency of the object. In Barton's pendulum system, one of the pendulums was the same length as the driver pendulum. This one started to oscillate much more than others because the frequency of the forced oscillation was its natural oscillating frequency. Yes, you can ask a question. Yes. Yes. You are moving. Once you are moving. If I lift you up and I let you go. If I pull you to the side and I let you go. When you get down here, you'll be on your maximum speed. All right. People, music instruments. For example, a guitar. And I'm not talking about electric instruments and all these funny things. But a normal guitar, it's got strings. And it's attached to a hollow box system. And if you pluck the string, the vibration is transferred into the box, and the box starts vibrating at the same frequency as that of the string. It's one of its natural frequencies. And that allows resonance to occur for you to hear the sound. If I spun a guitar string very tightly as it is on the guitar, and I plucked it in air, am I going to hear it? Hardly. Maybe very, very slightly. We can hear the sound from the guitar because every single string that you pluck causes a vibration of a specific frequency, and the box of the guitar is designed to have various natural frequencies that correspond with the frequency of the string. And that is why the sound is amplified, because the vibrating, the forcing frequency is the same as the natural frequency, and the amplitude increases. Yes? Yes. If you have a flute, just a normal ordinary flute, a straight flute with holes in it, what you actually do when you close and open up holes, you're changing the length of the column of air. You blow air through it. The air vibrates in the column. By closing certain holes, you change the natural frequency of the flute. And depending on the frequency with which you blow into the flute, it starts resonating. And that is the one that you will hear. Yes, yes, it's also just air moving along a column. All right, and when a resonance occurs, that is the sound that you hear. All right.
Hi there, parents. Do you have primary school kids and want them to get extra quality supplementary lessons to up their grades? Then simply switch to One Africa TV's #LearnOn1, where your kids can get maths, English and science lessons every weekday from 9 to 11 a.m. with repeats from 2 to 4 p.m. And thanks to NMH's MyZone, these lessons are 100% Namibian. There's so much to learn with #LearnOn1. Invite learning in.
Grade 12s. We have to carry on with the chapter on metals, and we've had a look at, we say, the stuff they dig up from the ground when they mine for metals. The ore is the rock containing the ground and the sand, etc. We said then that to get the metals from the ore, we have to refine, or we have to filter out some of the rubbish before we can get to the pure ore. And we said then the first step in that case would be to do a process known as froth flotation. They add foaming agents to this mixture. It's usually in a watery medium. They agitate it, it makes a foam, and the ore sticks to the foam. The impurities sink down to the bottom. Then once we have the purified ore, we have to go and look at the reduction of the metal from this ore. Okay, now this is a chemical process, and the reduction then of the metal from the ore, the process of reduction depends a little bit on the reactivity of the metal. The more reactive the metal is, something like aluminium, for example, is very difficult to extract from the ore, because if it's very reactive, it reacts very violently with oxygen, and it forms a very strong bond between the aluminium and the oxygen. For you to go and break the aluminium from that oxygen in aluminium oxide, you will require to put in more energy than what was given out when it formed. All right. So we have different ways of reducing the metal from this purified ore. Now, the first one that they do is just very simply, they go and heat the metal in air. Now, I think I've said to you already, why was there first a Bronze Age before there was an Iron Age? Because bronze or copper then is less reactive than iron. It's easier to reduce it from the ore. And it's as simple as, if you have the ore containing the copper, you simply heat it up exposed to air. And then the heat from the air causes the sulfur, it's copper sulfide, to be released. It forms sulfur dioxide, and, well, if it is copper, it will form copper and sulfur dioxide. The sulfur dioxide would be an impurity, a pollutant. All right. At Shumep mine, where they extract copper by smelting, there was lots of sulfur dioxide. They used to release it into the atmosphere. Nowadays, they catch it up. And what do they make from that sulfur dioxide? You must have seen the lorries going. At one stage, it used to be blue tankers. On the side of the lorry, it says sulfuric acid. Well done. Okay, people, sulfuric acid is used in the extraction of uranium from its ore. So they produce it over here. It's a waste product that they would have just released into the air. They produce sulfuric acid. They send it to Arandis, where they use it in the extraction and purification of the uranium ore. Okay, so if it is just copper sulfide, it's very easy to reduce the metal from the ore, because copper is fairly unreactive, and we will get copper and sulfur dioxide. This copper will not be perfectly pure, but it would already be in the form of a metal. Okay. Other ores, like iron sulfide, okay, iron pyrite, they heat it in air. It doesn't form iron metal, but it removes the sulfur as sulfur dioxide, and the iron recombines with oxygen, forming iron oxide. And the iron oxide can then be extracted in a process inside a blast furnace. All right. Iron is slightly more reactive than copper, so it's slightly more difficult to extract iron than what it is to extract copper. Now, when we have a look at the extraction of iron from its ore, the ore in which iron is mined is mainly iron sulfide, which then they heat in air, and it becomes iron oxide. And the iron oxide then is extracted. They heat it together with coke. Now, coke is not the cool drink you drink. Coke is a form of carbon, okay, like coal, all right? So they add coal to it. The coal burns. It forms carbon monoxide. Then a process happens. The carbon monoxide is converted to the carbon dioxide is converted to carbon monoxide, and the reaction between the iron and the carbon monoxide occurs. These two fight over the oxygen. We find that the carbon wins, so it forms carbon dioxide, and it releases the iron. Now we will go and have a look in more detail at the extraction of iron just a little bit later on. This is just a broad outline. The next step is a process called electrolysis. Now, electrolysis is actually a very expensive process, because you need to take the ore and you need to melt it, And sometimes the melting point is so very high that they have to add impurities to it because, for example, aluminium melts over 2,000 degrees. I think 2015 is the melting point for aluminium oxide. So they add impurities to it. They talk about a cryolite mixture is made, and this melts at a lower temperature. Okay, so you have to melt the ore. This requires energy. And then we need an electric current to be passed through this molten ore. That also requires energy. So electrolysis is a very energy-rich process, and we use this for the more reactive metals. All right? They say the more reactive metals, like sodium, magnesium, and aluminium, cannot be extracted by smelting. Now, smelting is the process we do in the blast furnace. Copper is extracted by smelting. Iron is extracted by smelting. Yeah, no, the process is smelting. Electrolysis then, only for the more reactive metals. We don't do it in this country. Our electricity is too expensive. There isn't enough electricity, so usually these ores are exported to countries, for example, like Canada, that have more electrical supplies, cheaper electricity, and they will extract these metals from the ores by electrolysis, and then we can buy back the metal if we need the metal for whatever industrial purpose we want. Yeah. Some of the metals that we work with are more well-traveled than what we are. Okay, because they have to be exported, taken out of the country, and then it is converted or extracted, and then from that point we can buy it back if we need it. All right. Now, the first major process that you need to know how it works is smelting. Now, there are two ways to do smelting. The one way is called an electric arc furnace. Now, in Shumep, we don't have an electric arc furnace. This electric arc furnace is slightly more sophisticated than the process in that used to be done at Shumep in the smelter there. All right, we'll have a look at that in a moment. Now, when we extract iron from its ore, the iron ore that we mine is mainly iron pyrites. It's iron sulfide. They say pure iron is very soft. Steel is iron with a small amount of carbon in it and making it harder and stronger. So the desk chairs are made from steel. Okay? In other words, it's iron containing carbon. Pure iron is soft. It's almost like lead. If you have a sharp knife, you can scratch a chunk out of a piece of lead. All right. Now, iron is also like that. Without the carbon, the iron is not very strong. The moment we mix the iron with carbon, it becomes steel, and steel has got varying grades of hardness and strength to it, depending on the amount of carbon. Now, there is a YouTube video which we can go and have a look on Wednesday afternoon when we have the double period. I'll go and show you some of them in one of the periods. The electric arc furnace, it's basically a very large container into which electrodes go. These are specifically carbon electrodes. In this furnace over here, they go and put in the iron ore as well as some scrap metal and some calcium carbonate. When current flows through these electrodes into this mixture over here in the bottom, it passes the scrap iron that they add to this furnace, helps with the conductivity in the furnace. So the current can flow through the system. As a result of that, it heats up because of the resistance in the metal. We find that the carbon electrodes start burning. They become red hot, okay, and they react with oxygen in the furnace, and certain chemical processes occur. If we look at it step by step, scrap steel, okay, recycling of steel. They add it into the furnace there where they extract the ore. All right, so scrap steel, the iron ore, which is usually iron sulfide that has been converted to iron oxide, Fe2O3. Fe, I think it's just FeS. All right. And limestone. Now, limestone is calcium carbonate. Large carbon electrodes are lowered into that furnace. We find that sparks jump between the two electrodes. Remember, the one electrode is positive and the other electrode is negative. All right. And if there is something that can conduct between them, the current will flow through the system. All right, from one electrode to the other. Then the scrap steel is placed into the furnace. It helps with the arcing process. The arcing process is when the spark jumps from the one electrode to the other. All right. This arcing process also causes heating. Then we find the carbon from the electrodes burn away. They form carbon monoxide. All right, there's the reaction. Carbon plus oxygen gives me carbon monoxide. When do we get the formation of carbon monoxide? Why not carbon dioxide? There's not enough oxygen. Remember, incomplete combustion will give us carbon monoxide. In this case, we want carbon monoxide. So this is a whole big furnace in which there's a lot of combustion occurring. There is some carbon dioxide, but the carbon dioxide reacts further with the carbon and it forms carbon monoxide. And the carbon monoxide reduces the ore to iron and carbon dioxide. The reaction would be iron oxide plus carbon monoxide will give me iron plus carbon dioxide. What impurity would be in this molten iron? Yes, we have carbon rods, carbon electrodes. They burn, they form. There's carbon monoxide in this combustion process. All right, so there will be some iron mixed with, or the iron will be mixed with some carbon. This is actually quite desirable. Why? To make steel. Okay. Now, when we go and have a look at the blast furnace, just in the next step, you will see that the blast furnace is a more crude, a more primary way of extracting the iron ore. With the carbon electrodes that they put into this mixture over here, they can, to a certain extent, control the amount of carbon in the steel. So this steel would be of a higher quality than what we get from the blast furnace. Here are just the reactions. The carbon monoxide reacts with the iron oxide, forming iron and carbon dioxide. This carbon dioxide goes back into or stays in the system. We find if carbon dioxide reacts with carbon, it forms carbon monoxide again. So this is all part of the production of carbon monoxide. The limestone decomposes. The limestone is the calcium carbonate. It decomposes, it forms calcium oxide and carbon dioxide. This carbon dioxide is part of the system, carbon dioxide reacting with carbon, forming carbon monoxide that reduces the ore. Now, the function of this calcium oxide reacts with impurities, the sand and the stuff, and it forms something called slag. Okay? Slag is the stuff that floats on top of the molten iron ore. And they can remove it because that slag contains impurities. All right. When you weld with the steel, weld steel with a rod, the outside layer of the rod has got a compound on it that reacts with impurities and oxygen, etc. And you knock it off with a hammer, you chip it off afterwards. This allows you to make a very strong metal weld because at high temperatures, iron wants to react with oxygen. And this stuff prevents that from happening. So you don't get iron oxide in your weld because then your joint where you welded will simply rust eventually. Okay. If we look at the extraction of iron from the blast furnace, here we have a diagrammatic structure of the blast furnace. It's a long, tall chimney. And they go and add the iron ore, the limestone, and the coke from the top. They pour it in. This whole system allows for air to travel through it so that combustion can occur. The coke burns. It causes the limestone calcium carbonate to break up. Here's the calcium carbonate. It breaks up, forms calcium oxide and carbon dioxide. The coke burns, it forms carbon dioxide. Why do we want carbon dioxide? Carbon dioxide will react with coke, forming carbon monoxide. And we want the carbon monoxide because the carbon monoxide will reduce the iron from the ore. Over here we find this carbon and that iron, they fight over oxygen. What happens is iron loses the fight, carbon wins the oxygen. Yes. Yes, well, in this sense. Okay. So carbon gains the oxygen. We say the iron ore is reduced to form iron. All right. Once again, the calcium oxide, what will that do? It will react with impurities, forming slag. The slag is usually floating on top. Here they show in the furnace. Over here is the pure molten ore, or metal we want. It's tapped off. And the slag over there is tapped off. Now, slag in itself is not totally wasted. They use it in building of roads. All right, part of the substructures. So just here, the bulleted points. Heat from the furnace causes the calcium carbonate to decompose. Carbon dioxide reacts with coke, forming our reducing agent, carbon monoxide. The carbon monoxide reduces is the term we use. The ore, the iron from the ore. The calcium oxide is the stuff that reacts with impurities. We refer to it as the flux. Calcium oxide is the flux that reacts with the impurity, and they form slag, which can be tapped off. The slag floats on top of the molten steel, and it can be removed. Yes. The steel that is formed in the blast furnace will contain lots of carbon. The one from the electric arc furnace will also contain carbon, but a smaller amount. Okay, so you have a higher quality steel from the electric arc furnace than what you do have from the blast furnace. We refer to this first impure product of carbon as cast iron or pig iron. Is there a use for that? Yes. Cast iron, we make drain lids from them. We make the three-legged pots that we cook food in from them. All right. But what do we know about this steel? It's very brittle. If I drop a lid of one of those iron pots, it breaks. Yes. Okay. Even though it is very strong, it is brittle because it contains lots of carbon. Excess carbon can be removed. They go and take this cast iron, they go and melt it down once again, and then they blow oxygen through this molten carbon. What's going to happen? The carbon is going to react with the oxygen, and it's going to form carbon dioxide, and you will be left with steel that contains less oxygen. And so you can keep removing it until it is at the level that you want it. High carbon steel, medium carbon steel, low carbon steel, etc. Okay, so they call this oxygen pipe that they bubble the oxygen through this molten cast iron. They call it a lance, and the molten steel is then cast into blocks called ingots, and or even steel bars sometimes. It depends on what the processing plant looks like. Then if you are a manufacturer of steel girders or whatever, you go and buy in the steel in the form of these ingots, you will melt them down and you will process them into the shape that you need them to be. That is the extraction of iron. Now the extraction of zinc is very similar to that of iron. We find that the ore that contains zinc is known as zinc blende, all right, and that is zinc sulfide. The first step, just like with the iron, is to convert this metal sulfide into a metal oxide. They simply do that by roasting the ore in air. They just heat up the ore exposed to the atmosphere. And we find then sulfur dioxide would be given off as a waste product. either released into the atmosphere, but better if they could catch it up and use it for a different purpose. All right. But it is a pollutant. The formed sulfur dioxide is a pollutant, but it can be used to make sulfuric acid. At Tsumeb, they used to just release it into the atmosphere. The soil around the area of the smelter is very acidic. They've discovered there are many of the waste products that even if they release it up into the air, if it rains, it settles down. The winds carry it in a specific direction and it tends to settle down. So nowadays they use the iron sulfur dioxide and they make sulfuric acid from it. Zinc oxide then, this stuff that we get over there, is heated with coke. Once again, we have got zinc oxide. It's heated with carbon. All right. What's going to happen? The zinc and the carbon are going to fight over the oxygen. We find that the zinc will release the oxygen and the carbon will react with the oxygen forming carbon dioxide. There's a problem with the extraction of zinc in this blast furnace. Zinc has a fairly low boiling point. So it tends to form zinc vapor, and where will the vapor want to go? Up and out, all right? And they don't want that because this is actually the metal that they're trying to extract. So what happens is as this vapor rises up a chimney, it is cooled fairly rapidly. One of the methods they use is to spray it with molten lead. And then it falls down to the bottom, it condenses, and we get molten zinc at the bottom of the furnace, which can be extracted. Very often, zinc is extracted together with the lead. Is this a problem? How would they separate the two? Yes, lead is going to be more dense, zinc is going to be less dense. So it will separate into two layers due to their density, and the first products can be tapped off from that point there. Lead is more dense, yes, it goes to the bottom, and zinc will float on top. All right. Once again, the lead and the zinc extracted by this process is not perfectly pure. It has to go on to a secondary process where they purify it further. Extraction of copper. The ore is concentrated. Then we heat it with coal, which is carbon, and sand and lime. We find that copper sulfide is formed. This copper sulfide is referred to as being copper matte, M-A-T-T-E. All right, while the impurities are removed as slag, that would be the function of the lime. It's going to react with the impurities forming slag. The copper matte is heated and it's converted into a crude copper metal called blister copper. Have you seen the lorries coming from Tsumeb with these large blocks? It looks like basins of copper in it, but when you look at it, you can see the copper is not pure. Okay, that is blister copper. And that has to be extracted or purified further by means of electrolysis. So it is exported. It's taken to Walfish Bay Harbour, where it is exported, and it is converted into pure copper by means of electrolysis. So by countries where there is cheaper electricity. And then when we need copper for wiring, for whatever we need it, we have to buy in the copper metal again. All right. Yes. Sulfur dioxide, once again, is a pollutant. What's one of the main pollutants from mining processes? Sulfur dioxide. All right. What does sulfur dioxide do to the environment? It's the main culprit causing acid rain. The sulfur dioxide dissolves in water and it forms sulfuric acid. And acid rain comes down and it causes the soil to become acidic. It damages microorganisms in the soil. All right. It eventually damages the waxy layer on plants and they can't grow and bear fruit, etc., as they should. So sulfur dioxide then is a pollutant together with arsenic. This is removed. Yeah, Arsene. This is removed, and the blister copper then is purified further by electrolysis. We do not do that in Namibia. It is too expensive, the electricity. It's cheaper to export it how many thousands of miles away and let them purify it, and then buy it in the purified form. All right, because our electricity is much too expensive. Yeah, they buy the ore. These refineries or processing plants, they buy in the copper ore, the blister copper from the copper producing countries. All right. I think I must stop at this point. What I do want to do, just want to go back over here. We talk about the metal is being reduced from the ore. And it's as simple as we start out with iron oxide and we end up with iron. So we've taken a lot of stuff and we've made it into something less. So it's reduced. But in terms of the scientific terminology, reduced is actually a reduction, which goes together with a process, all right, oxidation. Now, in grade 8 and 9, and I think in grade 10, we did reactions with oxygen. And we said anything that reacts with oxygen is an oxidation reaction. But even that is a limited explanation. Technically speaking, when I have a metal and it forms when a metal loses electrons, all right, we have oxidation. So the loss of electrons is oxidation. These electrons must go somewhere. All right? Reduction is a gaining of electrons. Now let's go and have a look at if I have iron oxide plus carbon monoxide, I will get iron plus carbon dioxide. Now, it's more difficult for you to see it at this point with the carbon, but if I go and have a look at this iron oxide, it's an ionic compound. Do you agree with me? And in this ionic compound, the iron consists of iron plus 3 and the oxygen minus 2 charge. So, if I go and have a look at the metal that is formed over here, is it in the form of ions? No, it's in the form of the metal. Hasn't lost or gained electrons. Can you see that? So we say this thing's oxidation state is 0. So for a substance to go from a plus 3 state to a 0 state, must it lose or gain electrons? It must gain electrons. Okay, it gains 3 electrons to get that. And if we go back to the definition of reduction, what is reduction? It is the gaining of electrons. If we go back and we're going to have a look at the carbon, can you see this carbon has got 1 oxygen, but there it's got 2. So it has reacted with oxygen. And what is a reaction with oxygen called? It is called oxidation. All right, now in one of the next modules that we will do, we will go and have a look at reduction-oxidation reactions. But for this work that we are doing with the extraction of metals, just understand that we say the metal is reduced